Let's start with what actually happened, because the real story is stranger than most of what's circulating about it. On October 22nd, 2025, Google's quantum AI team published a paper in the journal Nature that the physics world had been waiting on for over a decade. It wasn't framed as breaking physics. It was framed carefully and technically as the first verifiable quantum advantage in the history of computing. But strip away the caution of a peer-reviewed paper for a second and look at what the number actually says. Running on Google's Willow chip, an algorithm called quantum echoes solved a real scientific problem 13,000 times faster than the best classical algorithm running on one of the fastest supercomputers on Earth. Not a synthetic benchmark designed to look impressive. A real calculation, checkable against real laboratory results that no classical machine on the planet could match in a reasonable human lifetime. To understand why physicists are still talking about this nearly a year later, you need to rewind slightly further to December 2024, when Google first introduced Willow to the world. At that point, the headline number was almost cartoonishly large. Willow performed a benchmark computation in under 5 minutes that would take the world's most powerful classical supercomputer, a machine called Frontier, roughly 10 septillion years to complete. 10 septillion is a 1, followed by 25 zeros. For context, the universe itself is about 13.8 billion years old. 10 septillion years isn't just longer than the age of the universe, it's longer by a margin so extreme that the comparison stops being meaningful as a measurement of time and starts being a demonstration that you're looking at a fundamentally different category of machine. Willow wasn't just faster. It was doing something classical computers structurally cannot do at any speed, on any timescale. But here's the detail that made scientists take this seriously in a way they hadn't with earlier quantum announcements, including Google's own 2019 Sycamore demonstration. Willow didn't just go fast, it solved a problem that had quietly haunted quantum computing since the field began. Every quantum chip ever built has faced the same brutal trade-off. Add more qubits to do more powerful calculations, and you also add more opportunities for error, because qubits are extraordinarily fragile, easily disturbed by heat, vibration, or stray electromagnetic noise. For nearly 30 years, the assumption was that scaling up a quantum chip meant scaling up its error rate right alongside it, a vicious circle that made truly large, reliable quantum computers look almost impossible. Willow broke that circle. Google's team tested progressively larger grids of qubits, moving from a 3x3 array up to 5x5, then to 7x7, and at each step, instead of getting worse, the error rate was cut in half. That's just what physicists call operating below threshold, and it's the first hard experimental proof that a quantum computer's reliability can actually improve as it grows, rather than collapse under its own complexity. Now here is where the story most people are watching gets built, and where it's worth being precise, because this is the part that tends to get exaggerated into something closer to fiction. When you ask how a chip with about 105 qubits can process a calculation that would require more computational steps than there are atoms in the observable universe, you run directly into one of the oldest, strangest, and most genuinely unresolved questions in physics. What is actually happening? Physically, when a quantum computer computes? This isn't a fringe question invented by clickbait. It's a question that serious physicists, including David Deutsch, one of the founding theorists of quantum computing itself, have been arguing about for decades. Deutsch has long argued that the sheer scale of parallel processing inside a quantum computer only makes sense if you accept the many worlds interpretation of quantum mechanics, the idea that every possible outcome of a quantum event actually happens, each in its own branching universe, and that a quantum computer is, in some sense, borrowing computational power from those other branches. It is one of the most contested ideas in modern physics. Plenty of equally serious physicists reject it entirely, favoring interpretations that don't require literal parallel universes at all. Nobody has settled this argument, and Willow didn't settle it either. What Willow did was hand that decades-old argument a genuinely new, much bigger piece of experimental evidence to fight over. So here's where we're going in this video. We're going to walk through exactly what quantum echoes did in that Nature paper, including the real molecules Google used it to study, and why chemists at UC Berkeley are already excited about it. We're going to look at what verifiable actually means in quantum computing, and why that word is doing more work in this story than the flashy 10 septillion year number ever did. We're going to sit inside the actual scientific argument over what quantum computation implies about the nature of reality without pretending that argument is settled, because pretending it's settled is exactly how good science turns into bad mythology. And we're going to ask, honestly, what any of this means for medicine, for materials, science, and for how soon useful quantum computing actually arrives on a timeline you'll live to see. Stick around, because the actual science here is more unsettling than the exaggerated version you've probably already seen clips of. Let's get into the actual mechanics of quantum echoes, because the name alone tells you more than most headlines bother to explain. The algorithm works something like sonar, but built entirely out of quantum interference instead of sound waves. Google's own researchers, Hartmut Neven and Michael Newman, described it using an ocean metaphor that's genuinely useful here. Imagine trying to find a sunken ship at the bottom of the sea. Ordinary sonar can tell you there's something down there, a blurry shape, a rough outline. Quantum echoes is built to do something closer to reading the nameplate on the hull. Technically, the process is called an out-of-time order correlator, or OTOC, and it works by sending a kind of quantum pulse forward through a system of qubits, deliberately disturbing one of them, and then running the process backward in time to listen for the echo that comes back. Tiny, otherwise undetectable effects get amplified through quantum interference until they become measurable, revealing exactly how information spreads and interacts inside a complex quantum system. That is the whole trick. Not raw speed for its own sake, but a way of seeing structure that classical computers are mathematically incapable of resolving, no matter how much time you give them. Here's why the word verifiable in that October 2025 announcement matters more than the headline number. Google's earlier 2019 Sycamore demonstration was groundbreaking, but it drew real skepticism because the specific calculation it performed, essentially simulating a random quantum circuit, had no independent way to be checked against anything in the outside world. Critics could argue, reasonably, that you were watching an impressive parlor trick rather than proof of something new about physical reality. Quantum Echoes was built specifically to answer that criticism. Because the algorithm's output can be reproduced by running it again on a different quantum computer, and because it can be cross-checked directly against physical laboratory measurements, this is the first time a quantum computer has done something both faster than any classical machine and independently confirmable as accurate. That combination, speed plus verifiability, is what actually separates this announcement from every "we did something a supercomputer can't" headline that came before it. And Google didn't stop at a theoretical demonstration. In partnership with researchers at UC Berkeley, led by chemistry, Professor Ashok Ajoy, the team used the same quantum echoes technique to act as what they call a molecular ruler. Nuclear magnetic resonance, the same underlying science behind an MRI scan, has been the standard tool chemists use to map the physical structure of molecules, essentially figuring out exactly where individual atoms sit relative to each other in three-dimensional space. It's foundational to drug discovery, to materials science, to understanding how a new medicine might bind to a target inside the human body. The Berkeley team ran the quantum echoes algorithm on Willow to study two real molecules, one with 15 atoms, another with 28, and then check the quantum-derived predictions against results from traditional laboratory NMR. The predictions matched. More than that, the quantum method surfaced structural information that conventional NMR alone tends to miss, effectively extending the reach of an instrument chemists have relied on for decades. That's not a hypothetical future application. That's a working proof of concept, published, peer-reviewed, and reproducible, sitting on Google's website right now. Step back and look at where this actually points, because the significance isn't really about one molecule or one algorithm. It's about timeline. Google's own quantum hardware director, Julian Kelly, along with lab founder Hartmut Neven, have been fairly explicit in briefings that this progress is tracking almost exactly against a roadmap the company published back in 2020. A 6-stage plan that ends with what they call a large-scale error-corrected machine, expected to arrive sometime around the end of this decade. Willow, and the quantum echoes result that followed it, represents roughly the midpoint of that roadmap, the proof that error correction actually scales the right direction, and that a quantum computer can produce results useful enough and trustworthy enough for real scientific work outside the lab. And 2026 brought another quiet but important development. Google added an entirely new hardware approach to its research, a neutral atom system running alongside its existing superconducting chips, essentially a second bet on a different physical method of building stable qubits, hedging against the possibility that superconducting circuits alone won't scale all the way to the finish line. None of this, on its own, tells you what quantum computing means for how we understand reality itself. It tells you that a machine now exists that can perform calculations no classical computer ever will, in a form that can be checked against the physical world and trusted. But that achievement is exactly what reopened a question that has been simmering in theoretical physics for 40 years, a question that has nothing to do with drug discovery or materials science and everything to do with where, physically, all that computation is actually happening. That's the part of this story that gets genuinely strange, and it's where we're headed next. Here's the question that Willow and quantum echoes forced back into serious scientific conversation. And it's worth stating it as plainly as physicists actually argue it, without dressing it up. When a quantum computer with roughly 105 qubits explores a computational space larger than the number of atoms in the observable universe, and does it in minutes instead of septillions of years, where is all of that computation physically taking place? The chip itself is small. It sits in a single refrigerator, cooled to a fraction of a degree above absolute zero, occupying one location in space. And yet the mathematics describing what it's doing requires a number of simultaneous computational states that dwarfs anything that could plausibly be happening inside that one physical object, in this one universe, using any classical notion of where information lives. This isn't a new question invented to make quantum computing sound spooky for a YouTube video. It's the exact question David Deutsch, one of the founding theorists of the entire field of quantum computation, has been asking publicly since the 1980s and 90s, long before anyone had built a chip capable of demonstrating it at this scale. Deutsch's argument, laid out across decades of papers in his book, The Fabric of Reality, is that the only interpretation of quantum mechanics that actually makes sense of a quantum computer's power is the many worlds interpretation, first proposed by physicist Hugh Everett in 1957. Under that interpretation, every quantum event with multiple possible outcomes doesn't collapse into a single result. Instead, all outcomes occur, each unfolding in its own branch of reality. And these branches don't communicate with each other except through the extremely narrow, extremely precise phenomenon of quantum interference. Deutsch's claim is that a quantum computer, when it explores an astronomical number of possible states at once, is in some real sense distributing that computation across a correspondingly astronomical number of parallel branches, then collecting a single coherent answer back into our branch through interference. On this view, when Willow completed a calculation that would take 10 septillion years classically, the many worlds interpretation says you're witnessing the aggregated output of more parallel computations than there are atoms in the visible universe, all happening simultaneously, all invisible to us, except for the answer that returns. Now here's the part that responsible science journalism has to include, and that a lot of viral content conveniently leaves out. This is a genuinely contested interpretation, not a settled scientific fact, and plenty of equally credentialed physicists reject it. The Copenhagen interpretation, still the most widely taught framework in university physics departments, treats the collapse of a quantum system into one outcome as simply how nature behaves, without requiring an infinite branching. Multiverse to explain it. Decoherence theory, developed extensively since the 1970s, offers another explanation entirely, one where a quantum system's strange superposition states leak away into its environment through ordinary physical interactions, producing what looks like a single definite outcome without needing parallel universes at all. Nobel laureates and leading quantum information theorists sit on every side of this argument, and no experiment, including quantum echoes, has produced a result that can distinguish between these competing interpretations. That's the honest, unglamorous truth. A quantum computer's raw performance doesn't secretly prove which interpretation of quantum mechanics is correct, because all of the major interpretations predict the exact same measurable results. They only disagree about what's really happening underneath those results, and that disagreement, frustratingly, may not be something any experiment can ever fully resolve. What Willow and quantum echoes actually did was raise the stakes of that argument, not settle it. Before Willow, you could reasonably say quantum computers were small enough and their advantage over classical machines modest enough that maybe some clever classical trick was quietly making up the difference behind the scenes. After below threshold, error-corrected chip produces a verifiable result, 13,000 times faster than the best supercomputer on Earth. Checked against real laboratory chemistry, that argument gets a lot harder to make. The gap between what a classical machine can do and what Willow just did isn't a rounding error anymore. It's a chasm wide enough that even physicists who reject many worlds outright now have to explain, in their own preferred framework, exactly where that computational power is actually coming from. Some point to the sheer mathematical richness of Hilbert space, the abstract mathematical structure quantum states live in, arguing it doesn't require literal parallel universes. Just an extraordinarily large, extraordinarily real mathematical object that superposition genuinely occupies. Others argue that this is exactly the kind of edge case where our classical intuitions about where a computation happens simply stop applying, and that asking the question at all may be a category error, like asking what's north of the North Pole. Whichever side of that argument you land on, one thing is not actually in dispute. This is no longer a purely philosophical debate confined to physics journals and conference panels. It now has hardware attached to it, hardware that works, that Google is actively scaling toward a fault-tolerant large-scale machine by the end of this decade. And that raises the last, and honestly the most consequential question in this whole story: what happens when this stops being a laboratory curiosity and starts being a tool sitting inside hospitals, pharmaceutical labs, and materials science firms? That's exactly where we're headed to close this out. So let's talk about what actually happens next, because this is where the story stops being abstract and starts being concrete enough to matter to people who will never read a physics journal. Google's own framing, echoed by outlets covering the October 2025 announcement, is that useful, real-world quantum applications could realistically arrive within about 5 years. That's a notably specific claim from a field that has spent decades being cautious, sometimes to the point of vagueness, about timelines. The reason for the new confidence isn't hype. It's the Quantum Echoes NMR result itself, because it demonstrates something quantum computing skeptics have been waiting for since the field began. Not a benchmark designed to look impressive, but a technique that improves an actual working tool scientists already use every day. Nuclear magnetic resonance isn't a niche instrument. It's one of the core methods pharmaceutical researchers use to understand how a candidate drug molecule is shaped, and how that shape determines whether it will successfully bind to its target inside the human body. Materials scientists use the same underlying technique to characterize new polymers, next-generation battery components, and even the exotic materials used to build the very qubits inside chips like Willow. If quantum-enhanced NMR becomes a standard laboratory technique, and Google's Berkeley collaboration is a real working proof that the beneficiaries aren't physicists. They're the researchers trying to shorten the years-long, multi-billion-dollar process of getting a new medicine from a computer screen into a patient's bloodstream. It's worth being honest about the limits here too, because overselling this would betray the same instinct that turns real science into viral mythology. Willow has roughly 105 qubits. The machine Google's roadmap describes as the goal, a large-scale, fully error-corrected quantum computer capable of running long, complex algorithms without errors accumulating. Faster than they can be fixed is still, by the company's own account, a number of years away, tracking toward the end of this decade rather than arriving tomorrow. The Quantum Echoes NMR demonstration studied 2 molecules, one with 15 atoms and one with 28. That is genuinely impressive as a proof of principle. It is not yet the same thing as quantum computers. Routinely modeling the complex 1,000-atom molecules that define real drug candidates or advanced materials, the honest way to describe where we are right now is this: the foundational physics problem that made large-scale quantum computing look potentially impossible, the runaway error rate that gets worse as chips get bigger, has been experimentally solved. What's left is largely an engineering problem, scaling up a working principle rather than discovering a new one. That's a genuinely different and genuinely more solvable kind of challenge than the one the field faced even 2 years ago. The market noticed too, which is its own kind of confirmation that this wasn't just a physics community story. Alphabet's stock moved on the announcement, and coverage across financial and tech press treated the Quantum Echoes result as a credibility milestone, not just a research curiosity, precisely because verifiable is a word investors and scientists both understand the weight of. Meanwhile, Google isn't standing still on the hardware side either. In 2026, the Quantum AI team added an entirely new physical approach to its research portfolio, a neutral atom qubit system running in parallel with the superconducting chips that produced Willow. That's a meaningful signal on its own. Even the team with the current lead in verifiable quantum advantage is hedging its bet on the underlying hardware, because nobody, including Google, is certain yet which physical approach will ultimately scale all the way to a truly large, fully fault-tolerant machine. Competing efforts, from IBM's superconducting roadmap to Microsoft's topological qubit approach, are all racing toward the same finish line from different technical directions. And it is genuinely too early to say which physical architecture wins that race. So where does that leave the bigger question we opened this video with? The one about parallel universes and what it means that a 100-qubit chip can outthink every classical computer on Earth combined. Honestly, it leaves it exactly where it's always been. Open, contested, and now backed by dramatically better experimental evidence than physicists had even 2 years ago. What Willow and Quantum Echoes proved isn't that many worlds is correct, or that reality is secretly a simulation, or that a hidden layer of the universe has been decoded. What they proved is that the mathematics of quantum mechanics, whatever it turns out to actually mean about the fabric of reality, produces real, checkable, useful power in the physical world, right now in a laboratory, verified against real molecules. That's a much more interesting place to end up than a manufactured claim about breaking physics, because it's true, it's happening, and it's still unfolding in real time. Here's the question worth sitting with as you close this video. If the same technology quietly reopening one of physics' oldest Debates about the nature of reality is also, right now, being aimed at drug discovery and materials science. Which outcome do you think actually reaches your life first? A genuine answer about what reality is made of, or a new medicine that exists because a 100-qubit chip found a molecular structure no classical computer ever could? Drop your take in the comments. And if you want the real science behind the next quantum computing headline before it gets buried under exaggerated claims, make sure you're subscribed, because Google's roadmap says the next major milestone is still coming before the end of this decade, and I'll be breaking it down the moment it happens.